Now let us discuss example 11, and let's apply mesh analysis here in this circuit. Okay, let's identify the two meshes here and assign mesh currents I1, I2, okay, and then assign currents and voltages on the resistors, okay. So since we have a current source here, we need to assign a voltage here, V, okay. The variable of interest here is total power dissipated, okay. So we need to find the total power developed, and the total power dissipated will be equal to total power developed, okay. Now let's try applying mesh analysis here. But before that, let's try to answer the following questions. What is the voltage across the 3 ampere source? All right, that's the question. So can we know the voltage across the 3 ampere source by some kind of law, like Ohm's law? The answer is no. There is no way to relate voltage to current on this current source, okay. So there is no explicit VI relationship here. So then V remains as a variable here. So V is a variable here. So such conditions are called super meshes, as we'll see in a moment, okay. Okay, let's apply node analysis here. Okay, so the first mesh, minus 18 plus I1 times 3, okay. So this current is I1, this current is I2, this current is I2, this current is I1, okay. Okay, so plus V plus I1 times 6 equals 0. The second, KVL minus V times I2 times 9 minus 15 plus I2 times 2 equals 0, okay. So mesh analysis variables are I1 and I2. However, we have this extra variable V, okay, which is the voltage on the current source. So this means we need one more equation, because we have 3 unknowns, I1, I2, and V, but 2 equations. So the extra equation comes from the mesh relation, right? This current source is in common between 2 meshes. So obviously this current source relates the 2 mesh currents. So when we relate them, I2 is in the same direction as the current source minus I1, which is the reverse direction as the current source, so equals 3. This is the mesh relation, all right? Okay. Let me write this to here, because then I shall add the two KVL equations. So I2 minus I1 equals 3. Okay, that's the mesh relation. So now this system of equations can be solved. Three equations, three unknowns. So the system can be solved. However, now I want you to realize that when we add these two KVL equations, what happens? So those V's cancel out, and we have minus 18 plus I1 3 plus I1 6 plus I2 9 minus 15 plus I2 2 times 2 equals 0. Right? So can you realize what type of equation this is? Actually, this is the KVL equation around the bigger loop, right? So KVL in the bigger loop, and that loop is called supermesh. So this loop is called supermesh, right? So when you write down this KVL equation in the supermesh, there is no need for this extra variable V, right? So together with this relation, mesh relation, the system can be solved, okay? So two equations, two unknowns. Okay, now let's repeat what a supermesh is. A supermesh appears when there is a common current source between two meshes, okay? So this is a current source, and it's in common between these two meshes. So then these two meshes together is a supermesh, right? Now we shall add this supermesh condition to our mesh analysis, okay? So let's move on to the same question, example 12, same question, but now we shall use this supermesh concept, right? So now our mesh analysis becomes complete, right? So when we consider supermesh conditions, our mesh analysis technique becomes complete. So let's perform mesh analysis here in this circuit. So let's assign mesh currents and then check for supermesh conditions. So this is a current source. It's in common between the two meshes. So yes, there is a supermesh here, right? So this means there is a mesh relation, which is I2 minus I1 equals 3, okay? So I shall write down a KVL equation in the supermesh. Okay, let's assign voltages and currents. So minus 18 plus I1 times 3 plus I2 times 9 minus 15 plus I2 times 2 plus I1 times 6 equals 0, right? So instead of I2 from here, insert I2 equals I1 plus 3, right? So when you do this, we have minus 18 plus I1 3 plus I1 plus 3 times 11 minus 15 plus I1 6 equals 0 minus 18 plus I1 3 1 times 11 plus 33 minus 15 plus I1 6 equals 0. So if you simplify, you have 20 I1 equals 0, I1 equals 0, right? And from here, I2 equals 3 amperes. Right? So the mesh current I1 is equal to 0, and I2 equals 3 amperes. So this means there is no current flowing in the first mesh. So there is no current on 18 volt source, on 3 ohm resistance, and on the 6 ohm resistance. So the current here on these 3 branches are 0. Okay, let's move on to calculate the total power dissipated, which is the variable of interest here. The total power dissipated equals, plus total power developed equals 0. Let's check the powers of each source. This is 0. The reason is that there is no current on the 18 volt source. The current on the 3 ampere source is minus 18 times 3, which is minus 54 watts. So what we have done is something like this. So this is the 3 ampere source, and V equals 18 volts. Due to KVL, right? In the first mesh, there is no current in the first mesh, and 18 volts is directly appears on the current source as well, since there is no current on the 3 ohm resistance and on the 6 ohm resistance. And this is due to passive sign convention, because the current here enters the negative terminal of V. Also, the power on the 15 volt source is minus 15 times 3, which is minus 45 watts. Okay, so the situation is like this for this source. This is 15 volts, and we have I2 flowing here, and I2 is 3 amperes, remember, and this is due to the passive side convention, right? So this is I2. So total power dissipated equals minus of total power developed, and this is 99 watts. Okay, so question solved, and we solved this question using a super mesh. Okay, let's move on to example 13. So the variables of interest are IA to IE, which are the branch currents shown on this diagram, circuit diagram. So let's solve this using mesh analysis. So let's assign currents I1, I2, and I3, right? Now let's look for super mesh conditions. There's only a current source here. There's a single current source in the circuit. So this may create a super mesh. So let's see if it's in common between two meshes. Yes, it's in common between mesh 1 and mesh 3. So this means there is a super mesh here. So where is the super mesh? So here is the super mesh. Okay. So this means there is a mesh relation here, and let's write that down. So here, look at the direction of the current source. It's going up. So I3 is in the same direction as this one, and I1 is in the reverse direction. So this means I3 minus I1 equals 4.3 ID, right? ID is a dependent source variable, and we shall take care of it later. Then mesh analysis variables are I1, I2, right? And let's say I3. Okay, however, we shall write down KVL equations in the super mesh and in the second mesh, right? And we shall also use the mesh relation here to solve for the mesh currents I1, I2, and I3. Okay, now let's write down the KVL equations. So the one in the super mesh is I1 times 10. Let's start with the 10 ohm resistance in the first mesh. Okay, so I1 times 10 plus the voltage on the 100 ohm resistance, I3 times 100 minus the voltage on the 50 ohm resistance. So it's minus, we go from negative to positive terminal. The current on the 50 ohm resistance is I2 minus I3 amperes times 50, okay, minus the current on the 25 ohm resistance is I2 minus I1 times 25 equals 0. Okay, so let's see what we have done here. Let's put down the currents and voltages. Of course, we should have done this earlier, right? So these are the currents and voltages on the resistors. So let's identify the currents. So this is I1, right? So this is I3. This current is I2 minus I3. This current is I2 minus I1. Okay, and this current is I2. Okay, so those are the currents in terms of mesh currents on the resistors, right? So we are using those in writing the KVL equation. So we have written the KVL equation for the super mesh, and now we shall write it. We shall write down the KVL equation in the second mesh. So in the second mesh we have minus 200 plus I2 minus I1 times 25, okay, plus I2 minus I3 times 50 equals 0. So these are the two KVL equations that we should write, right? Then we need to also use the mesh relation, which is determined by the dependent current source. I3 minus I1 equals 4.3 ID. And lastly, dependent source variable ID equals ID is the current on the 25 ohm resistance, so it is I2 minus I1. Okay, so from this set of equations we can find I1, I2 and I3, right? So using your favorite analysis method, find those variables, find the values of those variables I1, I2 and I3. Okay, now we need to find the variables of interest in the last step. So they are IA. IA, the current on the 10 ohm resistance is I1. IB, the current on the 200 volt source is I2. IC is I3. ID is I2 minus I1, and IE equals I2 minus I3. Okay, so question solved. Okay, let's move on to example 14. Okay, we shall use mesh analysis. And let's identify the meshes and their currents. So I1, I2, I3, and I4. Okay, the variable of interest is I alpha, which is here on this branch. So we have a current source here. First of all, let's check if there is a super mesh or not. This is a current source, but it's not in common between two meshes. Okay, so this is only in the first mesh. This appears only in the first mesh. So since this is 1.5 milliamperes, the current here is directly then 1.5 milliamperes, right? So there is no need to assign a variable for it. Then the mesh analysis variables are I2, I3, and I4, right? So we need to write down 3 KVL equations in the second, third, and fourth meshes, right? So let's assign our voltages and currents. Okay, and identify the currents. The current here is 1.5 milliamperes. The current here is I2. The current here is I4. The current here is I4 minus I2. Okay. The current here is I3 minus I1. And here it is I3, right? And this one is also I4. Okay, now let's write down our KVL equations in the 3 meshes. Okay, for the second mesh, we have minus 3I alpha plus I2 times 7K minus I4 minus I2 times 5K equals 0, right? In the third mesh, we have plus I3 times 4K plus I3 minus I1 times 3K plus 8 volts equals 0. Of course, I1 here is 1.5 milliamperes, right? In the fourth mesh, we have minus 8 plus I4 minus I2 times 5K plus I4 times 4K plus I4 times 4K equals 0. Okay. And we have this dependent source variable I alpha, and it is minus I3. Okay, so find, using this set of equations, you can find I1, I2, sorry, I2, I3, and I4, right? And lastly, the variable of interest is I alpha, which is minus I3. So, question solved. Okay, when we compare node and mesh analysis, we can say that you should know how to perform both analysis, right? Which is more efficient depends on the problem. Usually you select the one which generates least number of variables, and you learn which to use with experience. Node analysis is the one used more often because it's a bit easier than mesh analysis, because in mesh analysis we use imaginary currents. However, node values, node voltages are real, right? And in exams you'll be specified which one to use. Okay. Okay, that brings us to the end of this chapter. If you compare the two methods, node analysis and mesh analysis, we use KCL equations in node analysis, and we use KVL equations in mesh analysis. We solve for node voltages in node analysis, and we solve for mesh currents in mesh analysis. And for the super conditions, we have voltage sources that create super meshes, and current sources in mesh analysis may create super meshes. This must be super nodes. Okay.